Okay, so imagine you're a blockchain developer, right?
Yeah.
And you need this very specific tool, maybe like a super optimized way to verify signatures inside your dApp.
Hmm.
You basically have two ways you could go. You could like build every single tiny piece of that engine yourself, make it absolutely perfect for just that one job.
Right.
That's kind of like the custom circuit approach.
Exactly. The bespoke, handcrafted solution.
Or you could grab, say, a powerful general purpose computer, a virtual one, and just write software for it to do the signature checking.
And that's the ZKVM world. Using a pre-built, flexible machine.
Yeah, exactly. Both get you verifiable computation, but how you get there and what you can do with it, that's pretty different.
That's a great way to picture it, actually. And for developers, especially in the Ethereum space, getting your head around the difference between custom circuits and ZKVMs,
Right.
well, it's becoming really crucial.
Right, for building efficient ZK stuff.
Totally. So today, we're going to really dig into how these two work, under the hood. Look at the technical pros and cons.
And figure out, like, when you choose one over the other for your project.
Precisely. It really boils down to this tension, doesn't it, between getting that absolute peak efficiency with something custom built versus the flexibility and maybe faster development you get with these virtual machine environments.
Okay. Because fundamentally, they're both using zero-knowledge proofs, right? ZKPs.
Yeah, absolutely. You can think of any ZKP system as having sort of two main parts. There's the front end
Okay.
that takes your computation, your program, and translates it into a language the proof system understands. Circuits, constraints, polynomials, that kind of thing.
Arithmetization, right?
Exactly, arithmetization. And then there's the back end, which does the heavy cryptographic lifting, generating the actual proof, and importantly, verifying it quickly.
So the big difference we're talking about today is mainly in that front end part.
That's the key distinction, yeah. With custom circuits, you are literally designing a unique mathematical blueprint, a specific circuit for one specific program.
Like designing that engine for just one car model.
Perfect analogy. Whereas with a ZKVM, the front end is different.
Oh.
You're not building a circuit for your application.
You're building, what, a circuit for the VM itself?
Exactly. You build a circuit, or rather a set of circuits, that represents the entire virtual computer, its CPU, its memory access, its instruction set.
Wow.
And then the program you want to prove. That just becomes input data that this big VM circuit processes.
So back to the engine thing. It's like building a super smart robot that can follow instructions to build and check any kind of engine you tell it to.
Precisely. You just feed it different blueprints, different program bytecode.
Okay, that makes sense conceptually. So let's dig into custom circuits first. If a developer goes down this path, what are they actually, doing?
Right. So at its core, building a custom circuit means using these specialized languages. Circum is probably the name you hear most often.
Yeah, heard of that.
To describe your program's logic as, well, literally a network of wires and logic gates, like designing hardware almost.
Okay.
And because you're designing it from scratch for just one task,
Yeah.
the big potential win is performance. Huge optimization potential.
Because there's no overhead. It's just the pure logic needed.
Exactly. You have fine-grained control over every single step. You can squeeze out every last drop of efficiency, shave off milliseconds, minimize computational cost.
Which matters a lot on-chain with gas fees and everything.
Hugely important for some systems, yeah. Especially performance-critical stuff where every cycle counts.
But it sounds hard, like really involved. What are the downsides?
Oh, absolutely. The trade-off is definitely complexity and cost. Building these things and then, crucially, auditing them properly.
Right, the audit.
Takes a lot of time, a lot of resources. You often need deep expertise, not just in coding, but in cryptography, too.
So long development times.
Potentially, yeah. We're talking, sometimes years for complex stuff.
Right.
And the budgets can get pretty high, maybe even millions for big projects.
All right.
And then there's flexibility, or rather, the lack of it.
Ah, right, because it's built for one specific thing.
Exactly. Once you've built that circuit, it's pretty much set in stone. If you need to tweak the logic, add a feature, reuse part of it for something else, it can be incredibly difficult.
Why? What makes it so hard to change?
Well, the logic is effectively hard-coded into the circuit structure. Things like conditional branching, if this, then that, or dynamic loops, they can be really tricky and inefficient to implement directly in a circuit compared to regular software.
Okay, so you gain optimization but lose agility. Big time.
That's the core trade-off, yeah. Significant upfront investment, peak performance, but not very adaptable.
What about security? You mentioned auditing. Is it easier or harder to audit these custom circuits compared to, say, regular code?
It's interesting. Kind of depends.
Mm.
For very small, well-understood circuits, maybe proving knowledge of a key or something simple like in Tornado Cache,
Uh-huh.
their simplicity can actually make auditing more feasible. You can potentially verify every single constraint.
Oh.
But as these circuits get bigger and more complex to handle real application logic,
Yeah.
auditing them comprehensively becomes a massive challenge.
Especially with ZK tech moving so fast.
Exactly. The techniques, the potential pitfalls, it's a moving target. You need really specialized auditors, and it still takes a huge amount of effort to feel confident.
So given all that, the cost, the time, the inflexibility, the audit challenge, when would a team actually choose to build a custom circuit today?
It really shines for those highly specific, super performance sensitive operations, where squeezing out that last 5% of efficiency makes a tangible difference to the bottom line or the user experience.
Like core protocol stuff or really simple proofs?
Yeah, things like that. Maybe some fundamental cryptographic primitive or a very simple proof like, I know the pre-image to this hash. In those narrow cases, the performance gain might justify the pain.
Okay, that paints a clear picture for custom circuits. Now let's flip to the other side, ZKVMs. What's the core idea here for a developer?
Right, ZKVM, zero-knowledge virtual machines, take a totally different philosophical approach. Instead of a unique circuit per program,
Yeah.
you prove that a program ran correctly inside a general-purpose virtual machine, using ZKPs, of course.
So the VM itself is the thing represented as a circuit.
Exactly. The VM's architecture, its instruction set, how it handles memory, all that is turned into a fixed set of circuits. And your program is just input data that this VM circuit chews on.
Okay, so it's like the VM circuit acts as a universal proof generator for any program it can run.
You got it. It kind of democratizes ZK proof generation.
Yeah.
You trade maybe some of that absolute peak custom circuit performance for a massive boost in developer speed and flexibility.
Okay, so for me as a developer who knows blockchain but maybe isn't a deep ZK expert, what are the immediate wins with the ZKVM?
The biggest things are convenience and speed of development, like massively faster.
How so?
Because ZKVMs aim to emulate standard computing environments. This means you can often write your code in languages you already know, like Rust or C++min.
Oh, nice. Not Circum.
Right. And you can use familiar compiler tools, like LLVM, to turn your code into bytecode the ZKVM understands.
So faster iteration, lower engineering costs?
Absolutely. It dramatically lowers the barrier to entry. You don't need that super deep crypto background to start building ZK-powered features.
You mentioned Succinct's ZK Tendermint Lite client earlier.
Yeah, that's a perfect example.
Yeah.
Building a fully verified Tendermint Lite client using custom circuits would have been, well, a monumental task.
Yeah.
But using their ZKVM, SP1, they were able to achieve it much more quickly because they could leverage existing code bases and standard tooling.
That sounds way more practical for most projects. But how does the VM actually do the proving? You mentioned an ISA, an instruction set architecture.
Exactly. Like any CPU, a ZKVM has an ISA, the basic set of commands it knows how to execute: add, subtract, load from memory, store to memory, jump, etc.
Okay.
When you compile your Rust code, it gets turned into this sequence of low-level ISA instructions. And the choice of ISA is really important for a ZKVM.
Why is that?
Well, some ZKVMs use standard ISAs, like RISC-V. That's great for compatibility. Lots of tooling exists.
Like RSC0 does, right?
Exactly. Others, like Valuta, actually design their own custom ISA, specifically optimized for being easy and efficient to prove in zero knowledge.
Oh, interesting. So there's a trade-off there, too.
Definitely. A complex, feature-rich ISI might let you write compact code, but proving each complex instruction inside the ZK circuit might be expensive. A simpler ZK-friendly ISI might need more instructions to do the same task, but each one is cheaper to prove. It impacts the underlying circuit complexity and the proof generation performance.
Okay, can you just walk me through the life cycle? Like, I write my Rust code. Then what happens to get a proof?
Sure. So, step 1, you write your code, compile it down to the ZKVM's bytecode using its toolchain.
Got it.
Step 2, the prover system runs this bytecode using the VM logic. As it runs, it generates a detailed log of everything that happened, every instruction executed, every memory access. This is the execution trace.
Like a flight recorder for the program.
Kind of, yeah. Step 3. This is the arithmetization part. The front end of the ZKP system takes that execution trace and the definition of the VM circuits and turns it all into a huge set of mathematical constraints, usually polynomials. Basically, proving the trace matches the VM rules.
Okay. Translating the execution into math problems.
Precisely. Step 4. The ZKP backend takes over. It uses complex cryptography, snarks, whatever the system uses, to generate a compact proof that all those constraints are satisfied.
The actual ZKP.
The actual ZKP. And finally, step 5, verification. Someone else can take this small proof, the public outputs, and very, very quickly check if the proof is valid, confirming the program ran correctly according to the VM's rules.
That's quite a process, but it sounds like most of the really hard ZK stuff is handled by the VM infrastructure itself.
That's the out-of-the-box ZKP idea, yeah.
So as a developer, I don't need to be a cryptographer.
Pretty much. It's a bit like HTTPS, right? You can build a secure website without being an expert in TLS encryption algorithms.
Right. The browser and server handle that.
The ZKVM infrastructure aims to do the same for verifiable computation. It abstracts away the deep crypto details, letting you focus on your app logic.
Okay, awesome for developer experience, but let's talk performance again. Is there a big hit compared to custom circuits? Is it always slower?
That's the classic question. And historically, yes, general-purpose VMs often had more overhead, but the gap is closing.
Yeah.
Fast.
Oh, yeah.
Several things. A huge one is precompiles.
Precompiles, what are those? Like Solidity precompile?
Kind of analogous, yeah. Think of them as highly optimized, dedicated circuits within the ZKVM specifically for common, expensive operations, like hashing Keccak, SHA-256, or elliptic curve operations.
Ah, so instead of running those using the general VM instructions, which might be slow.
Exactly. The VM just calls out to this specialized, super fast, hardware-like circuit designed just for that crypto operation. It's like having specialized math coprocessors.
Okay, that makes a lot of sense. What else helps performance?
Things like lookup arguments, clever ways to prove relationships between different data tables efficiently. Recursion is also huge, proving proofs of proofs, which can compress computation. And of course, hardware acceleration for the proof generation itself is becoming more common.
So with all these optimizations, can ZKVMs actually match or beat custom circuits sometimes?
In some cases, absolutely. That succinct SP1 example with the Tendermint Lite client, they actually benchmarked it as being faster than previous custom circuit approaches, partly thanks to Plonky 3 and efficient precompiles. So the performance story is getting much, much better for ZKVMs.
Wow, okay. Precompiles seem key then. They sort of bring a bit of that custom circuit optimization inside the VM for specific tasks.
Exactly. They bridge the gap for those common performance-critical building blocks. Sometimes people call them gadgets or chiplets, too.
Okay. What about security with ZKVMs? Does adding this VM layer introduce new risks?
Yes, security is definitely a critical area and needs careful thought. Yeah. You've got interactions between the compiler, the ISA, the ZKP system itself, the verifier. Lots of places things could potentially go wrong.
Like what sort of things?
Well, first, every single instruction in the VM's ISA needs to have rock-solid constraints. If even one instruction's constraints are slightly off or incomplete.
Someone could fake a proof.
Potentially, yeah.
Yeah.
A malicious prover might exploit that gap to generate a proof for an invalid execution. Memory consistency is another big one. The circuits have to rigorously prove that when the VM reads from memory, it's getting the correct, most recently written value for that address. No cheating allowed.
Makes sense.
Then there's just correctly implementing the ISA behavior, like what should happen on division by 0 in RASCV. The ZK circuit needs to enforce the exact specified behavior, otherwise the proof might not match what would happen in a real execution.
Edge cases and errors need perfect handling.
Totally. And finally, the verifier code itself needs to be secure. If there's a bug in the verifier, an attacker might craft a proof that looks valid but actually isn't, maybe bypassing checks or manipulating state.
Have people actually found bugs like these in real ZKVMs?
Oh yeah. Security audits have definitely turned up potential issues in various projects. Things like missing constraints, subtle verifier logic flaws. It highlights just how crucial rigorous design, formal verification efforts, and ongoing auditing are for these complex systems.
It really sounds like a vibrant but also complex ecosystem. You mentioned RASC0, SP1, Volita.
Sure.
Are there others pushing things forward?
Definitely. It's a super active space. You've got RASC0 focusing on that standard RASCV compatibility, SP1 from succinct leveraging Plonky 3 and really pushing precompile performance.
And Volita with its custom ISO.
Right. Taking that bet that a ZK-specific ISA can unlock more efficiency, maybe at the cost of some compatibility. Then there's Jolt, coming out of A16's crypto research, which uses a different approach based on lookup arguments, particularly their lasso technique, aiming for different performance characteristics.
So lots of different architectural bets being placed.
Absolutely. Everyone's exploring different trade-offs between ISA design, proof system choice, precompile strategies, and developer tooling to build the best possible ZKVM. Valida's custom ISIS is particularly interesting because it's such a direct attempt to optimize the machine itself for ZK proving.
It feels like the lines are blurring a bit. If ZKVMs are using precompiles, which are like specialized circuits, is there work on mixing and matching more deliberately?
Yes, exactly. That's a really exciting area. People are realizing it doesn't have to be strictly either.
Like use a ZKVM for most things, but call out to a custom circuit for one specific, super hard part.
Precisely. Victor Graf from RSC0, among others, has talked about this idea of using custom circuits as specialized coprocessors or accelerators within a ZKVM framework.
How'd that work?
Well, the main program logic runs on the ZKVM, but when it hits a particularly demanding subroutine, maybe some really exotic cryptography or a complex simulation step, it delegates that work to an attached custom circuit optimized just for that task.
And how do they, talk to each other securely?
There are different ideas being explored, maybe simple public inputs and outputs between the VM and the circuit, or potentially more tightly integrated approaches using shared memory arguments, though that introduces its own complexities around consistency and trust. Each method has trade-offs.
So it's moving away from ZKVMs versus custom circuits?
Yeah, I think so. It's becoming more about a spectrum of solutions. ZKVMs are getting incredibly powerful and flexible, and they're going to cover, I think, the vast majority of use cases.
But custom circuits still have a place.
Probably, yeah. For those absolute edge cases where you need the ultimate bare metal performance, they'll likely remain relevant. But with better precompiles, custom ISAs within VMs, and these hybrid approaches, the distinction gets fuzzier all the time.
This has been super helpful for getting a clearer picture. Thanks.
Hmm?
So if we were to wrap this up, what are the key takeaways for a developer trying to decide which path to explore?
I think the main thing is that trade-off. Developer experience and flexibility versus raw specialized performance.
ZKVMs win on DevX. Custom circuits can win on pure speed for a single task.
Pretty much. VKVMs mean faster development, lower costs, using skills you might already have, more adaptability. Custom circuits offer that potential peak optimization, but at a much higher cost in time, money, and rigidity.
So the best choice really depends on your project.
Absolutely. What are your goals? How mature is the project? What resources do you have? If you're early stage, iterating fast, ZKVM is probably the way to go.
Yeah.
If you're optimizing a critical, stable, high-value process, maybe you investigate custom options.
Okay. And looking ahead, as ZKVMs keep getting better and faster, what's the big question we should be thinking about?
I think the really interesting question is, will ZKVM advancements, better precompiles, faster proof systems, maybe even AI helping design circuits, eventually get so good that they largely make fully custom circuits obsolete for most practical purposes?
Or will there always be a need for that hand-tuned custom approach to hit the absolute performance ceiling?
Exactly. Will custom circuits always be the Formula One car, even if ZKVMs become incredibly capable SUVs that handle 99% of journeys? It's something developers should keep an eye on, watching how both sides evolve.
Definitely food for thought. How these tools shape the future of dApps and verifiable computing.
For sure.
Well, this was a great deep dive. If you want to explore more, definitely check out the projects we mentioned, RSC0, SP1, Valida, Jolt, and keep up with the research. Thanks for joining us.